Okay, so once again, starting with the same slide that the previous set of videos ended on, is there a way, the question is, given that you have a phase-space plot, okay, first of all, how would you have a phase-space plot? You would have a phase-space plot because you have some data. And so if you have multivariable data, multidimensional data, you basically could do the phase-space plot. So now the question is there a way to recover or at least estimate the phase space of a multidimensional system if you have a phase space plot? So that's what we're going to look at. So the answer is yes if you use something called delay embedding. So Florence Takens showed that the method of delayed embedding sufficiently will reconstruct a time series. Now the reconstruction is not an estimate, it's just an estimate, it's not perfect. So what the method does is you take a signal and you delay it, and then you use that new delayed signal as a new dimension. And each additional series is going to be delayed by a multiple of that chosen delay tau. So if I have some signal and it's 30 seconds long, and I let tau be 1 second, then I would have one signal that started at t equals 0, and then I would have another signal that started at 1 second, or that was delayed by 1 second, and I'd have a third signal that was delayed by 2 seconds. And each of those will be thought of as representing a new dimensionality. Now, this comes about, and really to understand this, it's easier to think of things in terms of fractal dimensionality, which we haven't really covered yet. But basically, what this is saying is that there is a self-similarity within the signal. And how the self-similarity works is that if you go to a smaller and smaller scale, the signal looks like it looked at a larger scale. And so you're making some implied assumption. By using this delaying technique, you're giving yourself some idea of what that scale or dimensionality is. So I'll try to illustrate that later with better illustration, and we'll come back to this idea of delayed embedding. But as far as the algorithm, how the algorithm works is you take some time series, x sub n of n, and you reconstruct that into a multidimensional time series where the higher order dimensions include a greater and greater delay. And so there is a routine that your author has included as part of the textbook called delay underline embed that's intended to perform this operation where the inputs are the one-dimensional time series, the embedding dimension of the n-dimensional vector, and the delay. And then y gives you a matrix of vectors that give you the system in embedded space. So how do you know how many of these delayed signals you need to include, where m is the number of signals that you have? If d is the system dimension, then basically your m should be 2 times the dimension, where d would be the true dimension of the system. So it's almost like the sampling theorem. You need twice as many delayed samples to reconstruct a signal with dimensionality d. And theoretically, tau your delay can be any number. But in practicality, you just need for m to be sufficiently large. And that's something that you can determine by trial and error. And tau can be neither too large nor too small. So every delayed vector should have some correlation to the previous vector, but not too much. So that sounds kind of like a non-answer. So let's look, for example, at a system, a classic system. So this is, you watch the water wheel. It was a Lorentz wheel. These are basically the Lorentz equations. So this is giving equations for position x, y, and z with velocity in the x direction, the y direction, and the z direction, respectively. So you have this this relationship with dx dt and x and y, dy dt and x, y, and z, and dz dt and x, y, and z. So you have these 3 equations, and we're just using this because it represents a lot of physical systems, including fluid flow and is used a lot to describe natural processes, and it illustrates things nicely. So if you set some parameters, um, and the parameters, let's go back. The parameters would be sigma, rho, and beta. So picking sigma rho, specific sigma rho, and beta, you see that the phase plot in this case is not two-dimensional, it's actually three-dimensional. So instead of plotting x versus y, we're plotting x versus y versus z. So each one of these points on the plot represents, for a specific value of x, y, or z, uh, where basically it represents for a specific point in time what are x, y, and z. So basically then you would be tracing out this path, kind of looks like a butterfly. You'd be tracing out this path as time goes on. And so notice there is not what we would refer to as a limit cycle. There's no circle or sphere where your points would be constrained. They're not approaching you can't really tell that from this, but they're not approaching a stable node because this is going sort of back and forth in this butterfly pattern. It just continues to sort of trace that out. So it's kind of a classic problem in nonlinear chaotic dynamics. Now, I want you to visualize something before we go to the next slide. Let's say that you were to take this figure and project it in two dimensions onto the XY plane. If that were the case, then it would turn out that there would be certain points that would appear to be fairly close together, but in fact they're not. So for example, this point here and maybe this point down here. If I were to project those onto the XY plane, they might almost lie right on top of each other. But in fact, there's quite a bit of separation between them in the Z dimension. So the point is, if you don't have a high enough dimensionality, those 2 points will look like they are nearest neighbors when in fact they are not. So just keep that in mind as we now discuss different methods of finding the delay. So how do you find the delay and how do you find the dimensionality? So actually, it could turn out that your delay and the best value for M, your delay, you have a little more leeway. And so it may be that there may be a range of delays where this will work. One way to do this is trial and error. It's fairly simple. Another way to do it is to look at the lag where the autocorrelation drops to 0 or to near 0. So in other words, if there is a lag where I have a 0 autocorrelation, then that means that there is some self-similarity in the signal at that particular lag. And then finally, to look at something called mutual information drop, and that's covered later on in the textbook. So those are ways of finding the delay. Here are some examples of different delays being used to represent that Lorentz system. You can see that 6 turns out looking pretty good, but there's not that much difference between 6 and 10. Quite a bit of difference between 1 and 15. So you can get a feeling for sort of where is your range where the system looks stable. Now, how do you find the embedding dimension? And that's a little bit more difficult. So we don't know the dimensionality of our system. So 3 different options. One is trial and error. The other is the false nearest neighbors method. And the third is principal component analysis. So we've talked about principal component analysis. Let's talk a little bit about false nearest neighbors. So this is what I talked about earlier when we were looking at the figure. So if you have a properly unfolded phase space, then the points in that phase space have specific nearest neighbors. If you don't use enough dimensions, so for example, on that XYZ plot that we looked at, if we only use 2 dimensions, then some of the points that are actually separated by quite a lot will appear to be close together in the XY plane. So what we can do is we can look at the ratio of the change in these, and so they would look like they were nearest neighbors, but that would be false. So what we can do is, as we change dimensionality, we can look at the number of nearest neighbors and examine the ratio of the change in false nearest neighbors. We can estimate a reasonable dimension that's embedded into the system. So the distance between two vectors can be defined using the Euclidean norm or the Euclidean distance. And sometimes we can use the max norm, which is maybe computationally more efficient. But this is basically the formula for the Euclidean distance. It's just the square of the difference in the vectors, square root, or the magnitude of the vector difference between vector A and vector B. So in MATLAB, there is an algorithm that, given your signal, your delay, the number of dimensions that you want to test, and the distance that should define nearest neighbors, you can then get the number of nearest neighbors. And as you change the number of dimensions, then the ratio of nearest neighbors will change. So a good starting point for what defines a nearest neighbor is if you take the standard deviation of your signal and take 10% of that, then that's a place to start. So if we look at different dimensions, different possible dimensions, and we look at the average number of false nearest neighbors, we find that for a single dimension we would have 0.35. And then we see a big drop off to probably about 0.01 when we go from 1 to 2. Another big drop off, or reasonably big drop off, when we go from 2 to 3. And then it flattens out, and there really is negligible change. So what this says is that probably the dimensionality of this system, a good approximation, would be to approximate this as a three-dimensional system. So that's how the nearest neighbor system works. Principal component analysis is another option. Basically, you could use PCA to determine the number of your principal components, and then use that as your estimate for n, because then that would mean that the other components in the system were not probably not related to the physics of the system. So here is an ECG signal. Principal component analysis is performed on that. Here is our scree plot. We're plotting eigenvalues versus n, and you can see that from 1 to 2 to 3, we have some fairly big drops. 3 to 4 is fairly stable. 4 to 5 is another drop. So just depending on how specific you want to be, you could probably estimate this as a two-dimensional or a five-dimensional system. So you might want to look kind of both ways. Here is what the author looks at. He looks at 3 dimensions. And in this particular case, the delay was found by using the autocorrelation method, and it was taken as 381 samples. And so you can see what the ECG looks like when you use a three-dimensional unfolding of the system. So this would mean that there are like 3 components of significance in that EEG system. We can go back and look at his scree plot again. 1, 2, 3. I don't know that I would have chosen 3, but the thing is, 3 dimensions we can actually plot. 4 dimensions you can't really plot, so I guess it makes some sense if you're going to do this plot that you might want to do it in 3 dimensions. So we're going to end this particular video on that point. So just to summarize, what we've looked at is we've looked at nonlinearity. We've looked at how to estimate dimension and delay so that these kinds of phase plots can be accurately done.